In part 2, what we want to do is the same thing that we had before. I'm going to erase a little bit of this over here. Make sure I'm still on the screen. Is we had our constant acceleration equations. Remember those? They were x is equal to x naught plus v naught t plus 1/2 at squared, v equals v naught plus at, and v squared equals v naught squared plus 2a x minus x naught. That was for linear motion, motion in a line. But what we want to do is convert this to angular motion. Notice it's mostly just converting the variables. So in terms of x, we don't go a distance, now we go an angle. So x becomes, so for angular constant acceleration, I'm just going to replace x with theta. So this is theta is equal to theta naught plus v naught, but v naught becomes omega naught times t plus 1/2 alpha t squared. So all I've done is convert from linear variables to angular variables. Same thing here, but this becomes omega is equal to omega naught plus alpha t. And the last one becomes omega squared is equal to omega naught squared plus 2 alpha theta minus theta naught. Now we do have to realize there's a convention with this, meaning that what we do is an object, if it's spinning counterclockwise, it's positive. If it's spinning clockwise, it's negative. You don't have to do it that way. Remember, the physics works no matter what, but to be the same as everybody else, it's easiest if you just make counterclockwise positive, clockwise negative. That's true for the velocities, the acceleration, and the distances. So you got to make sure you put in the right signs when you put it into these equations. But these will be the equations you use for constant acceleration, constant angular acceleration. And then you just got to figure out which ones to use at each time. All right, so basically you need these equations, all of these equations, know all this. And if you knew all that, then you can handle angular motion. It's not that hard. It's just keeping track of what variables and what everything means.